Memorizing a list of energy stores is the absolute fastest way to drop a full grade boundary on your 0625 Paper 4. I know that sounds crazy, but it's a massive trap. Today, we are completely destroying that myth and transforming your raw textbook knowledge into the exact, high-scoring, examiner-friendly answers that Cambridge actually demands.
So why does normal revision fail here? You walk into the exam, you see a 4-mark question on energy. You list off kinetic and thermal, and you still get 0. Why? Because knowing the physics isn't enough if you don't know how to speak the examiner's language. The mark scheme is never just looking for a simple keyword. It demands that you precisely track how energy moves, using exactly the right verbs and nouns. We're talking about a level of precision that most students just completely miss.
Section 1. The two-student duel. Flawed versus top-band answers. Let's look at a classic exam day mistake and pit two real student answers against each other. This is exactly where we separate the average grades from the absolute top-tier responses.
This brilliantly illustrates the difference between a vague, 0-mark guess and a top-band answer. Look on the left. The flawed answer says, the battery gives the bulb energy. Now to you and me, that sounds completely logical, right? But to a Cambridge examiner, it is scientifically empty. It gets 0 marks. Now look at the right side. The top-band answer says, electrical current transfers energy from the chemical store to the internal energy store of the bulb. Notice the difference? It precisely tracks the transfer from one specific store to another, and it explicitly names the vehicle doing the moving. It leaves no room for doubt.
To guarantee you always write that top-band answer, you must systematically follow this exact 3-step framework. First, identify the initial and final energy store. Where does it start? Where does it end? Second, identify the transfer method bridging them. How does it get there? And third, use exact Cambridge vocabulary. It's concept, evidence, and scientific examiner wording. If you miss even one of these steps, you leak marks. Now, in a moment, I'll show you the examiner clue hidden in a simple data table that changes your answer completely. But first, you absolutely need the framework that makes that clue obvious.
Section 2, the 4 methods of energy transfer. What's really interesting about this next section is how we can categorize literally every single energy movement into just 4 specific transfer methods. You don't need to panic and reinvent the wheel for every single question. You just need to select from these 4 pre-approved pathways.
Let's apply the framework. Take the source text catapult example on screen. When you provide the physical force needed to start something moving, you give it kinetic energy, right? Firing a catapult is a prime example of a mechanical transfer. But remember our 3-step framework. We need the exact examiner vocabulary to lock in those marks.
So here is the crucial point. Examiners are specifically scanning your paper for the phrase doing work whenever energy is transferred from one object to another by means of a physical force. Do not just write, "it pushed the rock," or "the catapult moved the stone." You must explicitly state that work is being done by a force. That phrase alone is the key to unlocking the mark scheme.
Beyond mechanical forces, you have to be ready to identify the 3 other pathways on the fly. First, transfers by heating, also known as thermal working. This is where energy naturally spreads from hot objects to cooler surroundings. Second, transfers by radiation, like infrared and ultraviolet light reaching Earth from the sun. And third, by electrical currents, where electricity acts as this incredibly convenient vehicle, moving energy from a power station, or a battery's chemical store, straight into a bulb's internal store. 4 pathways. Memorize them.
And when you're dealing with radiation, you need this exact Cambridge definition hardwired into your brain. It is energy transferred using electromagnetic waves. If they ask you to define it, that is the exact phrase you write down. No fluff, just the pure physics definition.
Section 3, the trap. Events versus processes. Let's escalate things and move to a nuanced distinction where students constantly trip up, confusing a rapid event with a prolonged process. Now, this might sound like a minor English language debate, but I promise you, it directly impacts how you describe energy flow on your exam paper.
Contrast these scenarios. On the left side, we have striking a match or falling over. On the right, the match burning or a person climbing a mountain. Striking a match is an isolated, instantaneous incident. It happens in a flash. Whereas the burning that follows is a continuous series of actions.
Let's lock in the strict definition so you don't get caught out. An event is instantaneous. It is something that happens or takes place, usually at a highly specific time and place. This means the energy transfer you're analyzing occurs in a sudden, very tight window of time.
A process, on the other hand, is a series of actions or steps
taking place over a long period of time. This means the energy is continuously transferring or changing stores throughout multiple steps. Understanding whether you are analyzing an event or a process helps you accurately describe the timeline of the energy transfer. If you describe a slow process as a sudden event, the examiner instantly knows you don't fully grasp the physical reality of the situation.
Section 4. The Examiner Challenge, Table 6.2. I want you to step into the shoes of the Cambridge examiner right now. We are going to apply our entire framework to real physical clues. Let's see if you can actually translate what your eyes see in an exam scenario into the physics vocabulary that scores the marks.
Look at these physical clues extracted directly from Table 6.2 in our source material. Material changing shape, an object changing speed, a chemical reaction, a change of temperature, nuclear fission, or changing the distance between objects. These are the exact real-world observations you will be given in your exam questions. Your job is to link them to the invisible energy stores. I want you to pause and predict your answers right now for these two specific clues: object changes speed and change of temperature. Connecting these physical actions to their correct changing stores is the exact open loop we talked about earlier. It's how you secure maximum marks. Okay, got your answers? Let's do the examiner correction. If an object changes speed, you must write that the kinetic energy store is changing. If there's a change of temperature, it is the internal or thermal energy store that is changing. By mastering this specific table, you instantly translate a real-world clue into top-end scientific vocabulary without even breaking a sweat. So you now have the ultimate system to perfectly explain simple energy transfers and replace that old memorization myth. But here is the massive problem you still face. What happens when that energy doesn't just go from point A to point B, but branches out across a massive, inefficient power grid in a highly complex Sankey diagram? If you can track energy changing in a single match, how do you track it across an entire city without losing a single joule, or worse, a single exam mark? That is the ultimate test of your 0625 mastery, and it is exactly what we conquer in our last 7 days revision map. Watching that next explainer is absolutely mandatory if you want to bulletproof your exam strategy. Click the video on the left side of your screen right now to master Sankey diagrams, and hit that button on the right to subscribe. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. See you in the next one.